Guys, did you manage to do all the questions? Let's start off with Eason here. Eason, how much do you get the potential and kinetic energy for position two? Like I said, that is one, two, and three.
98,000 joules.
98,000 joules is correct. Basically, you found that here is basically mgh lah, right? Which is going to be 50 multiplied by 9.8 multiplied by 200. Then you have gotten. Eh? Wait, this here is 98 Position 2 here also 98 meh, wait. Here is 98000, right? This is calculation for this position here. What about this position here?
Divide 2.
Yes, you're supposed to divide 2 because here is 100% ma. 100% was when it was 98,000 joules, right? Then here, what happened was half of it was converted into kinetic energy, right? So you divide by 2 lah. So 98 divided by 2, you'll get exactly 49,000 joules, right? Amo, you understand what I'm talking about? Jolie, why are you late, Jolie?
I was showering.
Shower earlier next time, my friend. Anyways, hey, what about the second one? Velocity here. Hayden, how much you get?
I got 44.3.
Good, 44.3 meters per second. Make sure your answer is in three significant figures. And finally, this last question here, Jolie. I see that you have done the homework. Excellent. You're supposed to get 62.6 meters per second. Anyone of you guys got a different answer for the first three questions? The first three questions here? Can anyone cannot do or not? If can do, I'm gonna move on. Of course, we got quite a few things to cover again today. Yeah. Hey Jolie, you have a question, right? You said your mom said that you had a few questions you couldn't do. Which questions was it? Later you let me know when we're done with this discussion. Okay. Hey, we move on if you're all okay. Then after that, this type here, they ask you what type of energy is possessed at ball at position X here. Since once again, I want to mention that there is height involved, it must be energy due to Eason was the answer. What type of energy?
Gravity.
Gravity. What's the full name of that energy?
Gravitational potential energy.
Very good. So the first one, A, you're supposed to get gravitational potential energy, right? Then after that, number two, give another position where the ball possesses the same energy of X. This one maybe it was not structured so nicely lah, but it's actually supposed to be Z because at Z it will have gravitational potential energy also. So this one here you just write Z. And then after that, they ask you to calculate the energy possessed at X and also at Z, right? Which is very straightforward. I think most of you guys did it. You're just basically going to go MGH. The first H you put 20, the second H you put 12, then you press in the calculator, you'll get something. Hayden, what is that something for 1 and 2?
Oh, 589
Joules.
joules and then 353 joules.
Do you guys both get the same answer? Huh? Yes, Okay, then after that, they ask, this is a very straightforward question. They ask you why is there a difference in the energy for both of these? Is simply because gravitational potential energy depends on your height, right? So if there is different height, then you will naturally have different types of energy. Jolie, I see your answer. You wrote the difference, but they're asking you, sorry, not where, why. Why is there a difference in the energy? Because there is a difference in the height, guys. Okay, then you'll get your marks already. Okay, guys. Anyone has any questions from these two part here? Can I? Okay, anyways, we're going to move on to the next part here. We still have power, efficiency, and energy resources. Once we're done with this, you can start doing all the rest of this as homework again this week. But let me try to cover this. I'm scared. I'm scared of a bit behind schedule because yeah. Yeah. Anyways, moving on. So this next part here, power is the rate at which energy is done. Right. So from here, all you need to see is the keyword here is you see the word rate again. By now, I hope everyone knows that power is basically equals to energy over time, right? Whenever you see the word rate, it's basically something over time. In this case here, they say work rate at which work is done. It means to say, if I want to translate this directly into formula, it's basically power equals to work done over time. I know some schools, they will teach you that power is equals to work done over time, but in reality, the real formula is energy over time instead. Why? Because this energy could be any type of energy that has a form of calculation, including work done, including gravitational potential energy, and also including kinetic energy. So the scenario is like this. Some students, they're damn stupid one, right? They'll say that, so the question will be something like, oh, right now I have mass of 50 kg and I have velocity of, let's say, 10 meters per second. And the time taken to complete all these things is, let's say, 20 seconds. Find the power for me, right? So some students are damn stupid, right? They'll say that, teacher, I cannot find this, of course, power is work done over time, which is damn stupid, right? In reality, you should know that power is equals to energy over time, depending on the question given to you, right? Depending on the information in the question, you're supposed to know what type of energy is substituted here. Since I have mass and velocity, then obviously in this scenario, it should be kinetic energy over time, right? Which makes the formula of power equals to half mv squared over t. Because once again, this energy could be any type of energy. For now, it could be work done, it could be potential, it could be also kinetic. Later, when you learn more in the syllabus, you'll know that power could be heat energy over time. Later on, you could also learn that it's electrical energy over time. So it's not only limited to work done. Do you guys get what I mean or not? Anyone don't understand what I'm talking about or not? Especially later on, I'll know. I mean, you will know later on when you
So
see.
like work done is basically power equals to energy over time.
What? Work done? No. Power is equals to energy over time. This energy could be any energy. It could be work done. It could be potential energy. It could also be kinetic energy. You said work done is power equals to energy over time. That's wrong. It's this here I'm trying to tell you is that power is energy over time. This energy can be any form of energy. Work done, potential energy, or kinetic energy. You get what I mean?
So based on the question, what they give, then we use the energy that can be solved with.
Yes, correct. Correct. I give you another scenario. Let's say in the question, they give you mass, they give you gravity, and they give you height, and they give you time. Then you ask to find power, then in this case here, it will be mgh over t lah, because this is energy and this is time, which boils back down to the basic understanding that it's energy over time. You get what I mean?
Yeah.
Okay. So yeah, but the definition is rate at which work is done, right? Which is the reason why a lot of teachers they teach work done over time. It's correct, it's not wrong, it's not the entire truth only. Okay? So obviously the faster we do the same work, the more power is released, and the slower we do the same work, less energy is released. A common example is literally running the same flight of stairs upwards or walking slowly same flight of stairs upwards. You'll notice that you're definitely going to be much more tired running up that flight of stairs is because For the same amount of work done to carry your body upwards, you're using less time. And because you're using less time, you'll be outputting more power, which makes you tired. Okay. And obviously, you're using more energy also when you run up them fast because you have greater kinetic energy as well, right? So all this is the reason why more power is used. Anyone don't know what I'm talking about? Anyone want me to repeat anything or reiterate anything that I've talked about? Good, 100%. By the way, what's the units for power? Hayden, do you know?
Joules per second.
Okay, the derived units is joules per second because this is joules and this is second, right? But the real the real units for power is watts, because watts is joules per second. Okay, in your exam, if let's say you really cannot remember the units for power, you can write joules per second. You are not wrong, but the better practice is to remember that power is watts, which is W. Okay. Please copy everything down here and start attempting the 3 questions at the bottom. A quick one, less than. You have 10 minutes to attempt everything. Hurry up. Done, ladies and gentlemen. Huh? Starting off with Jolie, how much do you get for your work done for A here?
2100.
2,100 joules. So 准 Correct this one. Do you guys get the same thing? Okay, the next question I want to ask, Jolie, do you convert this into meters?
No, I did not.
So you used, what was your working? Can you read out your working to me?
50 times 12 over 10 times 35.
50 times 12 over
10
10,
times 35.
35. Yeah, this will be wrong. Because unlike density, for work done, in order for you to get joules, your distance for force times distance must be in meters. It cannot be in cm. So if anything, it should be like 50 times the distance, which is 0.12 multiplied by 35, because there's 35 steps, right? Over a total of 10 seconds. This should have been your working.
Mm.
From which you should have gotten. Wait, two of you guys also did the same thing, Huh? Oh wait, two of you guys got the same answer,
I got 58.8.
58.8. You didn't even times the 35, did you?
35?
Yeah, there's 35 steps, my friend. Each step is 12 cm.
Oh,
50 times 0.12 times with 35, then only you divide it by 10. I think you're supposed to get 21 joules. Is it? Correct? Yeah, it's supposed to get 21 joules. Weird. I don't remember the answer anyway. Oh, it's not even, this is wrong. It's 50 kg, not newtons. Okay, guys, anyways, looking here, so this is the problem, right? The problem is that most of you guys do not write your working, from which you're supposed to get work done is supposed to be force times distance over time. Sorry, work done is just force times distance, right? So first information is that this is mass, right? So I need to convert this into force first, right? Which is W equals to mg, which is basically 50 times 9.8, right? Then you'll get something 50 times 9.8, you'll get 490 newtons, which is here, supposedly here, right? And then after that, your distance is basically 0.12 times 35, right? Which is basically 4.2, right? Then only you'll get an answer of 490 multiplied by 4.2. Oh, which is going to be 2,000 something. 2,058 joules. Correct? Anyone get this?
you also can use MGH.
MGH. Yeah, it'll be the same thing.
Okay.
But then again, once again, I want to emphasize that you should make it a good habit to write your answer in 3 significant figures. So your final answer should be 2060 joules, because your answer in the real IGs should not be more than 3 significant figures. Okay. Now after power is very straightforward, it's basically energy over time. In this case, here will be 206 watts. Yes, gentlemen? Kara. Okay, then after that, moving on to the next part. A new conveyor system, blah, 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 blah. It has a force of this, it has a distance of this, it has a time of this. You're asked to find the power again, which is essentially work done over time, which is essentially 890 multiplied by 12 over 22. This one was very straightforward. you'll get a very weird number, for which if you simplify it, it'll be 485 watts. You guys get this answer? Huh? Got. Hey, Jolie, got respond or not? Do you get this answer or not? Okay, last question. Last question here. Some of you guys might be a little bit confused because this one here is actually a little bit testing your deriving formula capabilities. So you have the first information, which is velocity, and you're given the force, right? And you're asked to find power. First and foremost, we once again go back to the understanding that power is equals to energy over time, right? Since there's force here, then most likely it will be force times distance over time. Then this is where a lot of you guys get stuck, right? Because you have force, you don't have distance, nor do you have time. But if you think about it, guys, if you think about it, right now, if you look at all these things here, right? Distance over time is velocity or speed. In this case here, I'm supposed to understand that power is equals to force times velocity. Because I take these two things and I combine them together. And ultimately, you're supposed to get 5,000 watts. Understand? This question is a bit interesting, but it rarely comes out in your exam, by the way. Okay, gentlemen, you understand what I'm talking about? Anyone don't understand what's going on? Want me to repeat anything? Okay, good. Moving on to the next part. Okay, second last part here. Right, so if you look at this part here, guys, we're talking about efficiency here, guys. And if you think about the word efficiency, I want you to think that efficiency means to say there's very little wasted material, guys. If something is very efficient, it means to say you waste very little things, okay? If I waste very little things, think about it this way, guys. Today, if let's say I have a chair factory. This is a chair factory, okay? And let's just say today if I put in 100 pieces of wood, is it possible to have 100 pieces of chair coming out of this factory? Definitely no, right? So in reality, maybe if let's say this is a damn efficient chair factory, maybe I can have 80 chairs coming out from the 100 pieces of wood, right? From here, I can roughly tell how much my efficiency is, right? If 100 pieces of wood go in and 80 chair comes out, assuming it's big pieces of wood, right? How much do you think the efficiency is, Ethan? Wait, Ethan, how much is the efficiency?
80%.
Good. It's supposed to be 80%. Why? Because right now, listen up, efficiency is given as, listen up, guys, it's important, output over input multiplied by 100%, right? And if it's output over input multiplied by 100%, essentially you'll get output divided by your input, which is 100 here, multiplying by 100%, which will ultimately lead you to 80% here. Okay. Now, is it possible to get an efficiency more than 100%? Possible. Jolie, is it possible or not? Possible. How come? How come it's possible? So
I don't know.
So you're telling me if let's say I put 100 pieces of wood in, maybe there'll be like 110 chairs coming out. Is it possible to have 100%, 110% efficiency? Now, let me tell you guys, while your parents tell you guys that you guys are perfect, right? Which is 100%, most of the time, they are lying, right? Because there is no such thing as 100% in the world, right? Uh, this means to say, whenever you do calculation in your exam and you get more than 100% efficiency, I want you to know for a fact that you are definitely wrong. And most of the time, it's because the students, they terbalik the output versus input. Like in this scenario here, maybe they'll put 100/80 multiplied by 100%. If I have a big number over a smaller number, for sure my efficiency will be greater than 100%, right? Which I can tell you is 100% wrong. It's 100% wrong. Okay? And because of that here, usually all you need to do is to bar it back upwards. Okay? So the golden rule here, listen up, guys, is basically you need to know that in order for you to calculate efficiency, the smaller number must be on top and the bigger number must be at the bottom. Then you'll get something that is definitely smaller than 100%. You understand what I'm talking about? Huh? Okay, I give you another dumb scenario lah, guys. Until the day, right, you can eat 5 kg of food and you can shit out 5 kg of shit, right? Until this day comes true, you'll never get a efficiency more than 100%. Even human beings can't process food at 100%. Okay, there'll always be wastage 100% for sure. Okay, guys, anyone has any questions for anything that I've mentioned so far? Oh, good. Please copy everything down and attempt the 4 questions at the bottom. You once again have 10 minutes. And gentlemen, you should be done by now. Let's start off with the first question, my friends. Aiden, what do you get for the first answer?
80%.
Oh, good. You're supposed to get 80% for the first one. And the second one, Jolie, what's your answer?
75.
75%. I think it's correct also. Please correct me if you're wrong, if I'm wrong on both of you guys. Number 3, Eason, what do you get for your answer?
25 joules per second.
25 joules per second. And finally, the last one here, Hayden, what's your final answer for question number 4? A. Question number 4A, what was your answer?
58.8.
58.8 is correct. And then Jolie, for your 4B, what's your answer?
73.5.
Yes, I think that is correct as well. Okay, guys, anyone got a different answer from what we've mentioned? Yes, okay, good, 100%, excellent. Guys, the last part here, before I throw you guys into the exercises once again. Listen up, This chapter always comes out in your paper 2, by the way, so please pay attention. First and foremost, we're talking about energy resources here right now. Did you know that almost all the energy that you see on Earth right now is originated from the sun? There are only 3 energies that do not come from the sun. Okay? The first one is called geothermal, which is, guys, listen up, you're not supposed to memorize this. Think about this. Geo means earth, right? Thermal means heat, right? Geothermal means to say heat from the earth, right? So where do you think geothermal comes from? What part of earth is responsible for geothermal? Ethan.
The Earth's core.
Good. The Earth's core is responsible for geothermal energy, son. The Earth's core is the reason why there is such a thing called natural hot springs, right? You don't need electricity. The water is still constantly hot because heat from the Earth's core is slowly sipping upwards to the water there, right? So geothermal does not derive energy from the sun. Nuclear, which is very straightforward as well, is basically talking about nuclear power plants, like uranium and plutonium that Japan has, right? Japan has all these nuclear power plants that produces energy, right? Nuclear is usually from uranium and also plutonium, which are both extremely radioactive. And finally, the last energy that does not derive energy from the sun is tidal. Where do you think tidal energy comes from, Hayden? Where do you think tidal energy comes from? Oh, Hayden, where do you think tidal energy comes from?
A sea.
The sea is where the tides are, but that's not where it comes from. What thing causes tidal energy change? Do you know or not?
Geothermal.
No. Okay, think about it this way. You all been to a beach before, right? When you guys go to the beach in the morning and at the night time, what do you notice?
The wave. The tides.
More specifically,
The tides are low and high.
good. There's low tides and high tides. Why? Because tidal is literally from the gravitational pull of the moon, guys. Do you know that because of the position of the moon, you actually pull the tides into low tide and high tides? That's why every time in the morning and night time, you'll see that the water level is different, right? Maybe like in the morning, you're playing in the beach, then the water is right in front of you. But at night, when you come back, the water is like receded backwards, or it's like super, super far away from where you were standing in the morning already, Low tide and high tide is due to gravitational pull of the moon, guys. Okay? So once again, these three energy resources don't come from the sun, geothermal, which is from the Earth's core, nuclear, which is from uranium and plutonium, and tidal, which is from the gravitational pull of the moon. They will ask you this in your paper 2 every year, consistently, right? You need to know these three energies don't derive energy from the sun. Every other energy comes from the sun. Fossil lah, wind lah, not geothermal lah, hydroelectricity lah, solar lah, blah, 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 blah. Every energy that you can think of comes from the sun, except for these three only. Okay? Yes, and then if you look at statement number 2 here, energy released from the sun is due to nuclear fusion. Fusion, which you'll learn later on, is when two hydrogen atoms fuse together to form a helium atom, which is the reason why the sun continuously burns over and over again, because literally generating energy on its own, known as nuclear fusion. Okay, what we have on Earth is nuclear fission. By the way, is fission. On Earth, fission is the one that is responsible for nuclear energy, right? Fission is literally the opposite. It's opposite of fusion. Fusion is two atoms joining together, right? But fission is one thing breaking into two. It's opposite of each other, guys, which you will be asked later on in your exam as well. Okay, fusion is the combination, fission is the separation. Okay. Yeah, then every other energy is something that you've seen before. Chemical energy is stored in fuel, water is from hydroelectric dams, geothermal from the Earth's core, nuclear fission, which is the reason why nuclear power plants can generate electricity, heat from the sun, and wind from windmills. All these are basic examples of types of energy that can be generated, right? The next thing you need to know is basically what's the difference between renewable and non-renewable. But as the name suggests, it's quite straightforward. Renewable means to say literally never run out on. It's renewable, right? Whereas non-renewable, like the name suggests, it will run out someday, right? Common examples of non-renewable energy is basically going to be fossil fuel and nuclear fuel. All this burn finish already, right? It will take millions, if not billions of years to reproduce again. So it's something that is obviously non-renewable. But all this stuff are renewable. You can't finish using the wind, you can't finish using wave, blah, 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 blah here. All cannot finish using. Okay? By the way, biofuel is basically things like wood, right? Which used to be alive, right? Trees are living things as well. Bio things, right? And if you cut down the trees and you can make fire with it, it's known as biofuel. Or sometimes, right, if you watch YouTube, you can see like sometimes scientists have been able to extract energy from cow shit. Those is a form of biofuel as well, basically from living things, and then they generate something. Those are called biofuel. Okay. In terms of renewable and non-renewable energy, usually in your exam, they'll test you on the advantage and disadvantages. While there is a common trait, the common trait between renewable and non-renewable, right? I do recommend every one of you guys read through everything here on your own free time, right? And really understand what's going on. Because in your exam, they'll sometimes ask you, what's the advantage of fossil fuel? What's the disadvantage? What's the advantage of this? What's the disadvantage? And so on and so on and so on and so on, right? It's not rocket science. It's literally quite common sense stuff, but you have to read through it to understand what's going on, right? But I can give you the general understanding, which is quite standard for all of it. For renewable energy, right, usually the advantage is it does much less damage to the environment. It doesn't produce greenhouse gases. But the problem is it doesn't provide much energy. For example, if let's say today the whole Malaysia goes solar, right? And sunny day, everyone can enjoy the aircon, the refrigerator and whatnot, right? Monsoon season come, everyone just live in the dark, right? Whereas non-renewable energy, while it does a lot of damage to the environment because it constantly produces carbon dioxide, right? It is ready to go on, right? 24/7, rain lah, monsoon lah, heat lah, blah, 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 right? Always got energy going on, right? So This is the reason why we still use non-renewable energy resources, because we need them to power our daily life. Okay. Oh, and one more common problem with renewable energy is the cost, the initial cost to set up is too high already. For any one of you guys who stay in landed properties, right? Maybe one of your parents might have asked for installation of solar panels into your roof to like save in energy, right? I've asked the quotation before. Just your house roof, which is like maybe 4 to 6 panels of solar energy, is somewhere around 30,000. I've asked before, right? 30,000 just for the size of your roof. Imagine those solar farms, right, that span the whole desert, right? That's crazy. That's like easily millions, if not billions. Probably not billions, maybe millions. Damn expensive, it's damn expensive to 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 start up the renewable energy resources. But yeah, this is one of the reasons why we don't fully go renewable as well. Also the limitation of our technology. Our battery can't store enough energy to release it. So, but then technology is improving now, right? So as you can see, Elon Musk here is like one crazy guy. He's constantly doing something on the renewable energy space. So it's quite interesting to follow him, although he's a bit psychotic. But then again, all the great people also a little bit psychotic on. If you're not psychotic enough, you can't be great, I feel. Okay, yeah. Anyways, this is all for today, guys. Please take your time right now to read through everything here, right? And even all these things here as well. Read through them, kind of know what's going on. And if you don't have any questions, you can start attempting these questions here already, at the bottom here. These are basically going to be your homework, all the way until you see 1.8 pressure. Then we're done with general physics already. Okay. Now, for Jolie, my friend here. Your mom said you have some questions, right? You want to ask them or not? Huh?
I think I know how to do already.
You said you know how to do or you don't know how to do?
No.
Really?
Mhm.
So you don't want to ask anything?
No.
Don't be shy, if you don't know.
No.
Okay, suit yourself. If that's the case, then start attempting the questions here.
Okay.
I'm going to be here until 7:45 in case anyone has any questions. So please, yeah, ask now if you have anything. Maybe I need to talk about one specific thing. Okay, everyone. Everyone, I want you to flip until you see this question. State the name of fuel that is burned to produce large amounts of electrical energy. You'll see this page here. I think most of you guys will not answer this if I don't say it out right now. Do you know how energy is generated in Malaysia? Who's our energy provider in Malaysia? You all know? Eason, you know or not? What's the name of our energy provider?
Isn't it like TNB?
Good, it's the Tenaga Nasional Berhad, right? Do you know how TNB generates energy in Malaysia?
No.
Okay, good. Everyone pay attention to this. This you will be required to draw this up because it's quite commonly asked in the exam as well. So sometimes the question will be something like this, right? They ask you to describe a process which electrical energy is obtained from chemical energy stored in fuel. You don't need to know like how we use fossil fuel to generate electricity because obviously we all know that we're supposed to burn the fossil fuel. But beyond that, I think most of the students don't know what's going on with the fossil fuel. So right now, I'm here to enlighten you. So starting from here. Let's say this is a fossil fuel. All right. It could be fossil fuel, it could be coal, it could be something. It's just fuel. Right. This fuel is actually used to create a big fire, like it's a big fire. This big fire, right, is actually used to boil a lot of amount of water. Okay, boil a lot of water. This water, once boiled, right, will actually produce high-powered steam. High-powered steam, which is actually used to rotate a turbine. I mean, the turbine doesn't look like this, but my drawing skills got a bit limited. Okay, it's used to rotate a turbine. This turbine is actually connected to a shaft, which is just a fancy term to say a stick, which is then connected to a power generator. This power generator converts kinetic energy into electrical energy. This power generator is similar to those that you see in the water dams. You know, like the water dams, they have water spinning this thing, right? They spin this thing. And then this power generator actually converts the kinetic energy from the movement to electrical energy, which is basically used to power up our whole cities. Okay. So from here, you need to know that yeah, in your exam, they'll ask you something like this. They'll say something like fossil fuel is used to generate a big fire, which is used to boil a lot of water. This this water is actually going to produce high-powered steam, which spins the turbine that is connected to a shaft that is connected to a power generator, which converts kinetic energy into electrical energy. Please copy this down somewhere that is empty in your notebook.
So like this happens in the
TNT stations. Yeah. But it's not so simple. It's like I'm like super simplifying the drawing. I'll show you a picture, I'll show you a video of what really happens inside. But you copy this down first to ease understanding. Done now, way. Why didn't anyone say anything? Okay, I show you guys the power generators first. So the real turbines, they look something like this, you know. These are the turbines that is spun by the high-powered steam. So these turbines that are spinning, right, is actually connected to magnets here and a lot of coils. You see like this red and blue color one. These are basically the magnets. And the coil that constantly rotate and cut through the magnetic field, right, it actually generates electricity. This is a chapter that you'll learn later on in year 11. It's known as electromagnetism, right? So basically you need to know that this turbine, as soon as you see, as soon as steam comes in, right, it'll spin like crazy, which is actually used to cut the magnetic field, which generates a lot of electricity, and output here will ultimately be current. The whole concept is that it converts kinetic energy into electrical energy. So I think there should be a simpler diagram. They don't have a simpler diagram. Whatever lah. I think my diagram is the most simple one lah. Easy to understand. Good. Okay, guys, any questions you want to ask? Good. Please attempt everything. You have the next 6 minutes to change your mind and decide if you want to ask anything. Okay, guys, I'm gonna stop class here today. Please finish up everything until you see this page here, my friends. All right. We'll discuss the answers next week and we'll go on to the last chapter of general physics, which is pressure. Okay, guys, I'll see you all next week.
Bye.
Bye bye.
Bye.